Hello everyone, today I will have a quick talk about the NASA InSight lander before it lands and a few predictions and what to expect. Now first off, for those who don't know yet, NASA's InSight lander is a Mars lander, a probe going to land on Mars a few hours from release of this video, so if you watch this video a long time after it's released, you can rewatch the live stream as it's recorded. If you watch it right now, then you can basically already switch to the live stream. But about that live stream, what can we actually expect to see? Well, not much. Obviously, data transfer from Mars is difficult. There are very low bandwidths. There are two experimental satellites flying alongside the InSight lander, which will not land on Mars, but also not fly past Mars, but turn into orbit around Mars and work as relay satellites, hopefully. They are experimental satellites, so of course we don't know whether they will work exactly as planned. They are actually a lot more experimental than InSight, which is built a lot more conservatively. If they work, we will get higher bandwidth of data than if they don't. If they don't, we'll only get data with a lot of delay from already existing satellites around Mars. If they do work, we get data with less delay, but of course we're still quite a distance from Mars and there's still the speed of light, so obviously we won't know whether it successfully landed until quite a while after it landed, and we won't be getting any live video either since the bandwidth just isn't high enough for any half-decent video transfer. What we will be getting is live data from the spacecraft, live navigation data, or, well, of course, delayed live navigation data, but live as in data sent by the spacecraft as it went through the atmosphere. And of course, as we're used to, that data will be put into a simulation, into a computer animation which we can watch, and we can see the acquisition of signal and such things in the control room. Then quite a long time after that we might see images, and well, it doesn't really have a video camera on board, but of course if you stitch together a few images you can get something resembling a time-lapse video with a lot of delay, since these images will basically be saved on the spacecraft's own computer and then a long time after landing be sent to a satellite in Mars orbit, which then will orbit halfway around Mars and then relay it to Earth. Now, in what to expect, another common question is of course how likely do you think it will succeed? I think it's actually quite likely to succeed, but we can't tell for sure. We can't tell how likely is, neither whether it will succeed or not. Mars landings are tricky for many reasons, both in terms of difficulty for the lander and in terms of difficulty to predict. One reason is simply that they're not very commonly done. There have only been, well, several, but not quite as many Mars landings as there have been, say, rocket launches. So trying to predict how likely one will succeed is based on limited data and limited experience. However, this one I think has a pretty good chance. It's not anything fancy or new. It basically uses a design based on a lander that already has been landed on Mars successfully a long time ago, and basically uses that same technology with a bit more experience and a few adjustments and improvements. And given that we've learned a few things since and haven't taken any major steps backwards, well, the Phoenix lander landed, so this one will probably too. Its descent profile and landing plan doesn't have any really crazy ideas and parts in it that would make it less reliable. It isn't trying out any new stunts or tricks. It's doing something that has been done before. It's going to do a powered landing after being slowed down by a drag chute and of course a heat shield. It will land a bit higher than the Phoenix lander in terms of elevation, which is of course a bit troubling. It means there will be less atmospheric drag, which means it will come in faster. And it also means that the atmospheric drag is harder to predict precisely. There will be a greater error of prediction, which means it has to do more adjustments perhaps. Of course, a few other things have changed from Phoenix 2. There are a few minor variables shifted, like it's coming in a bit slower, the spacecraft is a bit heavier. Those are minor changes that have to be adjusted for, but we also know exactly how to adjust for them. The technology has been slightly updated. All in all, it seems very promising. Now, another question, what is it actually carrying? Now, the spacecraft frame is based on the Phoenix lander, but that's just the vehicle, not the payload. InSight is carrying quite a few interesting things. Now, first of all, to get that out of the way, most well-known, most famously, it's carrying a silicon chip with the names of, I think, around 2 million people who signed their name onto the NASA website. I added mine, quite a few other space nerds I know also added theirs. I've heard some rather emotional stories about them. And of course this is quite fun and a great way to increase public interest, so great idea, NASA. But of course the main reason for the spacecraft are the scientific instruments. And the most notable ones of these, now of course there are some standard instruments which are just basically on pretty much any lander, and we'll just add another spot to our list of points on Mars where we have landed a basic lander and have basic information. But the main things that are really new here and that shape the design of the probe are the seismological instruments. Now, I've made a video about this spacecraft before when it launched, and Scott Manley has also made a few quite interesting videos about it, so I'll focus on what hasn't been discussed quite as much yet. What can we learn and what's so interesting about it? Now, of course, pretty much anything we learn in astronomy or planetology can be applied to many things. It can tell us many things, because due to basic physics, things are interconnected. If we know one thing and another thing, we can conclude a third thing. And so with all the things we already know about Mars, pretty much any new information gives us a whole lot of new things we can conclude from there. So every instrument is multi-purposed in a way. And there's a lot we can learn not only about the planet Mars as a whole, but even about the solar system as a whole from these geological instruments. For example, measuring Mars quakes could tell us how frequently asteroids impact Mars, which could tell us more about asteroids and how frequent they are in certain regions of space and how big a danger they might pose. But most interesting is of course what we learn about Mars and its past. The main question this probe is trying to answer is whether Mars has a molten core or a solid core, or how Mars core works at all. That's why it studies Mars quakes. Now that's physics again. You may have learned that in geography from earthquakes, that earthquakes are transmitted through the Earth's surface in different ways. So if you get hit by an earthquake and you're not standing exactly at the epicenter, you will be hit several times because the earthquake gets transmitted in several different ways, which go at different speeds and different rates, so different lengths. And by measuring those differences in time and differences in dampening, you can learn more about the physical properties of the inside of a planet. And of course there is the mole, which is, well, to simplify its purpose, it works as a drill. Although the functioning principle isn't that of a drill, the purpose is the same. You get a measuring instrument deep inside the surface of Mars. Deep for interplanetary research standards. Of course there have been much deeper boreholes on Earth, but in terms of how deep we have drilled in space, this would be a record, even though it's not actually drilled. It's hammered by a mole or electric nail or electric mole. It's quite an interesting piece of technology. It was actually developed by DLR, or the German Spaceflight and Aviation Research Center, together with the university I study at, so it's quite interesting. I've talked to the people who worked on it before, It's like many things in spaceflight, another example of a surprisingly simple concept that gets surprisingly complicated in its execution and detail. But essentially it has a metal hull, it's pointy at the lower side and it's heavy, so it naturally already kind of sinks downwards a bit. But to drive it deeper, there's a hammering mechanism inside, there's a heavy mass inside that hull, and a spring load mechanism. A single motor turns, and that drives the mass upwards against the spring, and then at some point it suddenly releases, and the spring rams the mass back downwards until it hits the lower side of the shell it's inside of, and thus hammers the shell downwards. This is repeated until the mole is several meters deep and can measure the temperature deep inside the surface of Mars. It can also measure temperatures while it's on the way down, and there's a thermometer on the surface, so we can compare the temperature at the surface and below the surface. So that tells us, is there a thermal gradient? Is Mars hot on the inside, which would slowly leak outwards and make the thermometer in the ground read hotter than the thermometer on the surface? How quickly do temperature changes on the surface translate to temperature changes down below, which tells us about the thermal conductivity of Martian soil, which might be interesting for people planning to settle on Mars someday in the far future. But it also tells us how quickly Mars might have cooled down in the past. And then of course you can wildly extrapolate. If you know how hot Mars is now, if you know how fast it cools down, you can get an idea of how hot it once was. And that might tell us, for example, whether it was once life-friendly, because in order to be life-friendly it needed a strong magnetic field. We know that today it no longer has a very strong magnetic field, which is part of why it doesn't have a thick atmosphere. There are several reasons for that. The low gravity also contributes. Of course, a low gravity means that it's easy for solar winds to blow off the atmosphere. It isn't held there very strongly. But also there's no strong magnetic field that protects the planet from solar winds, which allows those to blow off the atmosphere in the first place. And of course, if we know whether Mars once had a liquid core and whether it still does have a liquid core, and how much hotter it used to be than it is now, we can get a better estimate of how strong Mars' magnetic field used to be and how quickly it changed. Now, of course, all these informations about the inside of Mars are scientifically interesting and maybe useful someday in the far future, but indirectly they might also bring us closer to the really deep and interesting questions like, is there other life out in the universe? And no, it probably won't find any fossilized microbes, it doesn't have the instruments for that, but speculating about life in space is always a lot about statistics and extrapolation, and if we know whether Mars was once life-friendly at all, or whether it never used to be life-friendly, that already brings us closer to getting an idea of how common life may be out there. For now, let's hope the landing is successful. Let's also hope, we know the internet, some people have probably put joke names onto the NASA website and onto that silicon chip, but let's hope no one did anything too stupid so we can focus on the science and not on someone's idea of an internet joke taken interplanetary. So with that, thanks for watching, good luck InSight, and survive the landing.